So sec-butyl bromide. So if you don't know what it is, I'm going to draw it out. That is what it is. It's a secondary bromide. And then you have a sodium dioxide, which is a pretty strong reagent. It's not working. So the reagent alone, you can have E2 and SN2, both possible. If you look at this side, this is a secondary bromide. SN2 can happen, E2 can happen. So I actually don't know what exactly going on, but the point is, elimination is possible. And the question is not asking substitution products. So question limited out, no substitutions, just elimination. But substitution can happen too. Well, it's not an E1 because of the reagents are strong. I've been telling you, strong reagents don't wait for the E1 reaction. They just wait for the formation of cation, which takes time. They are not patiently, they're going to do things by themselves. So bromine comes off, make a carbocation. Yeah, that's the E1 process. That's not going to happen because of the reagent we have, they don't have a patience. They will just directly pull out the protons. The question is, which hydrogen it will pull out to make a double bonds? There's a hydrogen on that carbon. So with this base, I'm going to pick up that hydrogen and then double bonds can be formed. But if you look at the E2 elimination reaction, hydrogens are picked out by the base, you get the double bond formation, halogens are formed. So can this hydrogen be formed by the taken by the base? No, that's not the only reason. How many carbons do you need to make a double bond? Just one? Can you make a double bond with only one carbon? So you gotta think about which hydrogen base is gonna come after. This is a hydrogen of where the bromine is bound to. There's no way this can make a double bond by itself. That is not the right hydrogen. This is what I like to highlight. That is not the hydrogen can make an elimination. It has to be hydrogen in adjacent carbon, not on its own, right? Because a double bond cannot be made by just one carbon. I mean, it's pretty simple fact, but sometimes you just forget. So which hydrogen we're talking about? That is adjacent hydrogen, right? These carbons are right next to the bromine, so the base is gonna come, pick up this one, we're gonna make a double bond there. But that's not the only adjacent hydrogen. There's another one down here. So base, if the constant pick up this hydrogen, you're gonna have a double bond at that position. That's the E2 products. If the base come pick up this hydrogen, you're gonna form double bonds there. You're gonna form another E2 products. Between these two, which one will form more than what concept we need to use? Stability of the double bonds, right? Which ones are more stable? More carbon substituting ones are more stable. So that is a major product that can form, but it's going to be formed like 10%, 12%. I mean, substitution reaction can happen, but the questions are asking only elimination products, of which we not going to talk about. Now look at this one. 1-bromo 2-methylcyclohexane is that. The reagents are given is also strong base and strong nucleophile. That's a secondary, so probably E2 better in my point, because you got a tertiary carbon right next to it. I mean, it's not a quaternary, so that's not stopping SN2 reactions, but this gives a little bit steric hindrance. So SN2 can happen just like this one, but I would say less than this one, because these are more than the other one. So I think these are probably more likely to, even though we didn't specify only the elimination product. But the things go the same way. E2 elimination reactions, I can say E2 because of these are strong reagents, right? If that's not strong, I wouldn't say E2 at all. E2, you need to look at which proton it will come out, pick up. So first of all, this is an E1 process. You probably know already why that doesn't happen. because it is a strong reagent that are waiting. This all happens only when there's no strong base, no strong nucleophile. That's the only reason why this happens, even though it takes time. So this is not going to be our consideration because we have a strong reagent. It will just act out before the formation of the compound. So which proton? Those two are the adjacent protons. This one can be taken out, and then that one can be taken out. We will have a double bond with different conditions. If the base can take out the hydrogen on this side, you can have a double bonds here, which is that one. If the base can pick up this hydrogen, then you're going to have a double bond there. So two possible products for the elimination reactions. Which one do you think the major? The more substituting one, so you kind of know now what to go after. All right. It's pretty simple so far. Believe me, I'm building it up. Okay.
You say that wouldn't happen,
This one?
yeah.
Yeah, because we have a strong reagent. They're not just waiting formation of the compound.
You just not write the BR.
This is, I mean,
On the right, on the products.
on the green, the one we take it out?
Yeah, did you just not write that there?
No, I don't care about that. That's not getting really killed, right? So, yeah, we don't really care about the other side. And of course, it will happen within the solution, but goal writing is okay. Yeah. No, there's no carbocation, so there's no rearrangement.
Yeah, I'm sorry, what I'm saying is you can't rearrange E2s.
No, you cannot. There's no formation of carbocation between mechanics. So it's. All right, so it's kind of a similar question. I'm going to show you a bit different here. I mean, this is kind of a same similar question. What I'm saying, what you're saying is 1 bromide, 2 methyl, which is the same skeleton. The difference in the distance is there's a trans. Will that change the product?
Yes.
I mean, if not, then I'll probably be ask you so. But how it works, so we'll talk about this. Sense mean that those two on the same side. I mean, they both down, they both up. I'll just shoot the both with the wedges arbitrarily, just make a point that you can work with the both down with dashes, even make the same product anyway. Okay, so E2 elimination reaction. I'm saying E2 all because we have a strong base. I mean, ET has a small short notation for the F side, F, And organic chemistry use a lot of that, the F side, the F feels at ME, F feels at ET, that is kind of a standard short notations, but it's the same as the one that we used before. It's a strong base. So because of the strong leaders are given, I'm talking about E2 elimination, not E1, right? I would have to emphasize why we're not making carbocation because this is a strong reagent. They're not waiting for the carbocation formation. This is not going to happen, right? I know it's kind of what's hitting again and again and again. Like you need to hear the reason why I don't consider that. It's because the strong reagents are there. If it's not a strong reagent, then yes, carbocation is what is going to be formed to make anything possible, but not with this. Now we're going to talk about those two hydrogen is adjacent side. So either can be taken out by the base. If the base can take out this hydrogen there, then you're going to have a double bond just like what we did before, this one. Now you need to indicate that methyl with the wedge or dash, right? Because that's where we started from. On the other side, when this one come out to take out the base and proton by the base, then you're gonna make a double bond between those two, then you're gonna make this. The same as before. Which one will be the majors? The same thing before, double bonds have different carbon substituents. This one, di substitute double bond, 1, 2. That double bonds, 1, 2, 3. So more carbon substitute, the better, make it more stable. So this was a major, that's a minor, which is kind of a same answer that you had before. What I don't want you to draw, this is not the right way to draw. Why? This carbon is sp2 carbon. There's no wedge and dash in sp2. Wedge and dash is used for the sp3 tetrahedrocarbon. This is not a tetrahedrocarbon, right? So this is not the right way to draw it. Don't use a stereochemistry when you shouldn't use it. This is kind of okay with that. Not because of flatten, because it's sp2 carbon. Yeah.
And this, I think, probably the last question, but that bromine is lost in the products because it's like a concerted reaction, so it's pushing that bromine out when it's.
Yeah, bromine goes out with the electron, so it's going to be
Okay.
minus.
So, okay.
But that you don't have to write it down. That just speaks in the solution, but we don't care, but that's not getting down to it. Yeah. The base is a kind of a less susceptible to the state influence. When it acts as a nucleophile, that's something that you really need to care. Base can work somewhat remotely. Protein is very small. You can even pull it out somewhat in distance. The base, don't worry about the state influence too much, which will be talked about in chapter 7 for the very special circumstances. But now we don't have to worry about it, so that's not talked about that. All right, trends. So cis trends, what makes a difference is the stereochemistry of these two. That's only different. I mean, from the previous slide, you get that as a major product. Even with the cis form, you get that as a major product. So if you memorize this type of question, what would be the answer for this one? You're probably going to choose that one. And so far, those two other questions look similar to this, always have that as a major product. So that's the things that why I'm telling you, you cannot memorize that. Because if you choose that one as a major product for that question, because they look similar, no, that's wrong. So I'm going to show you why that is wrong. Anyway, with this, we got two adjacent hydrogen. I'm not going to talk about E1 because we already talked about strong base. It doesn't wait for the E1 carbocation formation, no E1. Either can be picked out. The base gonna come pick out this hydrogen, and then you're gonna make the more substitute double bond just like that one. Should we choose that one as a major product? Okay, most likely you choose if you don't consider the fact that each elimination reactions need a particular confirmation. What is it? So this is what I ask you to remember. As soon as you think about E2, something has to come to mind. Anticovalent or transaxial. This hydrogen and this bromine, they're both on the same side. They're not trans. You cannot make E2 relation with this cis hydrogen to the bromine. This is not going to happen because they cannot achieve anticovalent or the transdiaxial. So because the methyl groups are trans to the bromine, this hydrogen is there. Hydrogen is there, but that hydrogen cannot make an E2 elimination reaction. So that's why stereochemistry is really, really important. On the other side, you got the hydrogen opposite side of the bromine, which is the trans hydrogen, transaxial hydrogen is available. The base can't take it out, so that one's possible. That's the only product it can make. It's not making both. It can make only one. That's a net substitute double bonds, doesn't matter. This is the only one that can be made. The other one, not possible at all. So don't just think that, oh, that looks similar to what I saw before or what I seen the answer before. Similarity doesn't really matter in organic chemistry. I mean, it can probably help you to get things understanding, but you shouldn't rely on it 100%. Small differences, just the positional differences, whether cis or trans can change answer. Okay? So this is something that you really want to pay attention. We ask these questions a lot. You can clearly see that why. Because anything's possible between these two, but when I just change the stereochemistry, only one is possible. So that's only product really made. All right. What type of elimination this will be? You got methanol. Is a methanol strong base? Neutral alcohol is not a strong base, it's not a strong neutral bond. So will E2 elimination can happen with this? I mean, E2 is not possible because E2 plus a strong base. It's a weak base, so E2 is not possible. What is a kind of indicating that the formation of the carbocation is a silver nitrate, which is a kind of a added here to make the formation of the carbocation goes better. And also, it's not going to need it here, but a heat makes a molecule more energetic, so formation of carbocation can happen better, right? Heat makes SN1, E1 goes better. Because a carbocation is not an easy thing to make. So in order to make it, you got to provide energy. I mean, room temperatures, it can happen too, but if you heat it up, it will happen better. It will happen faster. So that's one of the ways to speed up the E1 SN1 reactions by heating it up. Or sometimes you're using silver salt, then you can basically, that will make a precipitate disappear. So this bromide, after left it, you can capture it, it will come back to starting material, but that will not happen because you disturb the equilibrium by making them precipitated out. So that's why the silver nitrates are used to promote SN1 E1 reaction. So that carbocation, we are expecting it forms. Then what happened to that? So what did I ask you to remember when you said carbocation? Rearrangement. So question is, will it rearrange?
No.
I mean, there's no hydrogen on that side, but there's a carbon. Methyl can also move too. If the methyl shift, you get the more substituted tertiary carbocation. So that happens. And then this one will have one hydrogen in this methyl group, and this hydrogen is the same as that one by the symmetry. And there's another hydrogen. So depending on which one goes out, you get the two equal products. If the solvent comes out, pick up the hydrogen from the methyl groups, then you get the double bonds placed between those two, which you move in that one. If the methanol comes pick up this hydrogen, you make a double bond between those two. That would be four. So question is, which one will be the major? The more substituted double bonds, right? That is a more substituted, that's less substituted. Can you make a